In the last class we talked about finding the derivative, and in today's class we're going to discuss more ways of calculating the derivative, more rules for differentiation. And this may be the first time we've used the word differentiation, and that just simply means that you're finding the derivative. It's the process of finding the derivative. And when we do this, the first rule that I'm going to go over is one that we actually kind of did in the last class, but didn't specifically mention it. Now, we'll apply a little bit more, but it's the same concept as what we did before, and it'll make sense in just a minute. Now, looking at this, the terminology here, this d over dx, of course, means you're going to take the derivative of whatever follows. And in this case, they say it's k times some function, where k is a constant. So, for example, here, the k in this case would be a 2. Think of it as a number, a constant, something that doesn't change. It could be pi, it could be 2, it could be 5, it could be whatever it is. As we do this, the derivative of a constant time of function, like 2 times x to the 5th, is the same thing as taking the constant times the derivative of the function by itself. Well, that's not too difficult to understand, and we'll just do an example problem here. The derivative of 2x to the 5th power, that means we're going to look at this constant first, this 2. So that means it's the same thing as 2 times the derivative of our f of x. In this case, our f of x would be x to the 5th. Now, we've already taken the derivative of x to the 5th, but if we were going to do this, we would say that it's 2 times the derivative of x to the 5th. The exponent is 5, so as you remember from last class, it's going to be 5x to the, you reduce the power by 1 to get 4. Excuse me. Now, of course, when we're working with this, that means that the derivative of this function is 10x to the 4th. Now, as you can see, this really isn't any more complex than what we've done before. If there's a number in front of the x's, we just simply multiply that number by the exponent that's there. So it adds just one step. It's relatively simple. Now, with this problem, we want to find the derivative of 5 times the square root of x. And when we're doing this, of course, we want to find the derivative, but we need to write the square root of x as an exponent. So, as by now I'm sure you're familiar, that's going to be 5x to the 1/2 power. Now, when I want to do the derivative of this, what I'm doing is saying I'm going to take 5 times the derivative of x to the 1/2. And when we're doing this, that's going to be 5 times 1/2 x to the 1/2 minus 1, which is going to be negative 1/2. So we get for a final answer 5 over 2 x to the minus 1/2. Now you're looking at this and saying, well, this makes sense. It's not too hard. Must I always write out the constant times the derivative? Well, not necessarily. A lot of students just simply do that in their heads. Now, if we take the derivative of this function, the derivative of minus 3 over x, if we separate the numerator and the denominator, we get x by itself. So when we're doing that, that's the same thing as saying I'm going to take the derivative. Now, take just the numerator, and let's put the minus sign with that as well, the minus 3. So it becomes minus 3, and of course we know that's 3 over 1. And then we'd say that's times then 1 over x. And when we do that, we've effectively separated the numerator and the denominator. We have the minus along with the 3, minus 3 here, and the denominator, the x is here, and of course there has to be something in the numerator, so it's 1 over x. Now we get this into the shape that we need it to be, that we're trying to find the derivative of minus 3x to the minus 1. Now when we're calculating this, This is the same thing as minus 3 times the derivative of x to the minus 1. So that's going to be minus 3. Now we take the exponent, the minus 1, and x to the 1 less power, minus 1 is minus 2. So this ends up being minus 3 times minus 1 gives us a plus 3, and x to the minus 2. So the derivative is 3x to the minus 2. Now, sometimes students say, must I really write this step out? I can kind of do it in my head. And that's okay. If you want to, you can. Realizing that back in the step back where we first calculated the first step, separated the numerator and the denominator to get this, what we're doing in that case is simply taking the minus 3 times the minus 1. Now, this isn't f of x, but I'm just going to write this in terms we're used to seeing, that the first derivative of this function, we would take minus 3 times minus 1, and then it's still x to 1 less power. Again, minus 2. So this becomes 3x to the minus 2. So we see the answer is the same. If you want to do it in your head this way, it's totally fine. A lot of people do. If you don't want to, please feel free to do it whichever way is best for you. Now, the next rule is saying that if you take the derivative of one function plus another function, that's the same thing as the derivative of the first function plus the derivative of the second function. Another way of stating that is to saying that the derivative of a sum, f plus g, is equal to the sum of each derivative. And this we've actually done before, we just didn't really talk about it. That, when we're working with this means that if we're taking the derivative of this 2x to the 7th minus x to the 5th plus 8, we can really break it down into the sum of each of the terms, and each term would be a function. So the first function, this would be like our f. So we're doing the derivative of 2x to the 7th. Using the first rule that we just learned, we know that's 2 times the derivative of x to the 7th. Now we're going to add to it our g, and our g is minus x to the 5th. So it's going to be plus the derivative of minus x to the 5th. And then now in this case we have an h, a third term or a third function here that's simply plus 8. So we're going to add to it the derivative of 8. Now when we do this, of course, 2 times the derivative of x to the 7th is going to give us 2 times 7 x to the 1 less power, in this case the 6th. Now we're going to take the minus, and of course the 1's not written here, but of course we know that it's there, so it's like minus 1 times 5. So we're going to add to it minus 1 times 5, x to 1 less power, which is 4. And we know that the derivative of any constant is, of course, 0. So we don't necessarily even have to write it, but we can. Now, putting all of this together, we will get 14x to the 6th minus 5x to the 4th. And again, if you don't want to use all of these steps, writing it down individually, you can. If you want to do it in your head, that's fine. Just make sure that you're familiar with it enough that you get the right answer. That's important, of course. Another example of this would be if we wanted to work with this particular function. Again, we can break them apart into the individual ones, but sometimes converting it over using our laws of exponents is more helpful. So we're going to do the derivative of x to the 4th. Now this becomes minus 3 over 1 times 1 over x squared. Well, of course, that's going to be the derivative of x to the 4th minus 3x to the minus 2. Now when we have it in this particular form, it becomes, again, easier to do. Now, if you want to do it in your head, you can quickly. You realize you can do it's going to end up being 4 times x to the third minus 3 times minus 2 plus 6 x to the minus 3. Or to break it apart and using all of the rules that we've learned, we would say that that this is equal to the derivative of x to the fourth. Now breaking apart the constant here, minus 3 times the derivative of x to the minus 2. And now the derivative of x to the fourth is going to be 4x and to the 1 less power, so that's 3. And then minus 3 times minus 2 gives us plus 6, x to 1 less power, or minus 3. So either way you want to do this, you can. If you would like writing it out because it's clear, that's fine. If you want to do it in your head, that's fine also. Now, a new rule that we haven't looked at all works with this kind of setup, where you have some function, g of x, and it's raised to a power. So this is different than if you simply had 4x squared plus 3x, because that's not, each of those terms are not raised together to a power. When we do this, to find the derivative of this kind of function, you take the exponent. This will feel very similar to what we've been doing before. You simply take the exponent times. Now with this, in this case, you're taking the entire function, the g of x, and you're raising it to a power that's 1 less than you started with, 1 less than r. Now, that in essence takes care of finding the derivative for everything outside of this g of x function, but it doesn't do anything about the derivative of what's inside. We need to include this, so that's why we take what we've just said and multiply it by the derivative of g of x itself. So the format is similar to what we've done. We've just added one step. Now once we do this, we also multiply it by the derivative of g, or in other words, we find g prime. So in doing this, this particular function we want to rewrite. Your laws of exponents, hopefully you remember. We're going to use them all throughout the course, so please get these down. They're very important. If we're going to do this, it's going to be the derivative of, now what we can do, it's like we could replace this with a parenthesis, like we did before. So it becomes 1 minus x squared, but it was the square root in the problem. Since it's the square root, we know the square root is to the 1/2 power. So now we have a function that's inside of a parenthesis, and everything inside of it is raised to a power. So we can't use the old way of doing it. We have to use this new law, this new rule. And that says what we're going to do is find the exponent. In this case, the exponent is 1/2. That's our r. So it's 1/2. Just to be clear, we got that from here. That's what our r is. So we put here 1/2 r times, now we list the function. That's 1 minus x squared. And the power of this g of x is 1 less than r. In this case, r is 1/2. So it's going to be 1/2 minus 1, which is going to be minus 1/2. Now we're not done. We also need to multiply this by the derivative of everything that's inside of the parenthesis. So far, we've been working with everything outside of the parenthesis. Now we need to take the derivative of what's just inside of it. So the derivative of 1, of course, is 0, and we find the derivative of minus x squared. Well, this is going to be minus 2x. Now, again, we don't worry about the 1/2 here because we've already taken care of it. We're looking at just the derivative of what's inside. this is 0. This becomes minus 1 times 2, minus 2, x to 1 last power, minus 2x. So now, of course, when we look at it, we realize, well, here the 2 crosses out. We don't want to forget here we have a negative, so we have to keep that there. So we get minus 1, which we don't have to write, and there's an x there. So we get x. I'm taking that from over here, of course. If you want to, just putting it into the normal order that we see. Minus x times 1 minus x squared to the minus 1/2 power. So that's a little bit more complex, but it's only adding one thing to what we've already learned. Now, here's another way of saying find the derivative, and that's simply saying to differentiate y, and y in this case is equal to x cubed plus 4x. Now, the x's are all in the denominator, the bottom of the fraction, and the 3's in the numerator. So again, we want to convert this over, and we can say that this is 3 over 1 times 1 over x cubed plus 4x. Now we've separated, but we still separated the numerator and the denominator. The x's are by themselves with the 1 over top. So we need to flip the whole fraction over. So think of it as we're going to put parenthesis around here and then flip the whole thing over. So this would become 3 times, again, it's going to be inside the parenthesis, the x cubed plus 4x. That stays exactly the same. Now, when we're doing this, before, we would say that there's a 1 there. We don't write the 1. It's simply what's inside the parenthesis to the first power. So when we flip this over, we put a negative sign in front of that. So it becomes minus 1. So y becomes equal to 3 times x cubed plus 4x minus 1. Now this actually adds something to it that we didn't list in the law, and that is if we have some constant before, we do the same thing as we did up here. It's the constant times f. So we're going to use this, but now our entire function we're doing with is this one. So we're going to combine this rule with this rule. So that means we take the 3 and multiply it by our minus 1. So the derivative, in this case, y prime, is going to be equal to 3, because that's the number in front of what's in the parenthesis, times minus 1, because that's our r, that's the exponent. And now we multiply it by everything that's inside of the parenthesis without doing anything to it. X cubed plus 4x. And the exponent that stays with that parenthesis is taken minus 1 in this case, and you subtract 1 from it. Minus 1 is minus 2. It's overlapping there a little bit, but hopefully you can still see that. Now, that's what we've done before in pattern, but we know with this new law that once we do that, we also have to multiply it by the derivative of just what's inside the parenthesis. Well, what's inside the parenthesis is this. What's the derivative of x cubed plus 4x? Well, we're going to multiply this by 3x squared plus 4. So this gets really hairy, but we would then could say that this is equal to minus 3, because we're combining the 1 and the minus 1. Usually we put something like this first and then this. I'm not too picky on that, but if we follow the proper order, then we'd say that this is 3x squared plus 4, and then we're multiplying it by the only term that's left here, this x cubed plus 4x to the minus 2. X cubed plus 4x to the minus 2 power. Now, of course, from here, because of the negative 2 exponent on just the x cubed plus 4x, If we need to put a value into it, for example, find a y prime of 3, we would have to convert this using our laws of exponents, but you know how to do that. We already did that in the past. If you don't have to use a value, then just leaving it in this form is the easiest thing, and it's quite okay. Now, just to kind of confirm this, what is the effect of a constant on a function? So if we had a function here, and starting with the blue one, it's x cubed minus 3/2 x squared, and that graphs like this. Now, if we add a constant to this, what that's going to do is for every y value we get, or for every x we put in, the y value will be increased by 2. So it's just going to push it up here before. We kind of talked about this before, but all that does is simply shift this blue graph up 2 units to here. So any place where we look at the slope, and again the slope is the derivative, it's going to be the same. At x is equal to 0, the slope would be, that's a horizontal line, it's going to be 0. It's the same there. If we do the slope here at minus 1, the slope is going to be like that. And we look at it and say, well, it's the same as it is here at minus 1 on the red one. If we look at positive 1, same thing. The slope would be a horizontal line both places. At 2, the slope would be kind of like that and like that. Looks to be the same. So again, that's why when we have some function plus a constant, it doesn't affect the derivative, and that's why we just ignore it. We don't have to take the derivative of a constant, or technically we're saying it's equal to 0. But now the effect of a coefficient does affect the slope. It does affect the derivative. Now again, the blue line is the original function, the same one we had before. Now if we take 2 times this function, that's going to change our values. And because we have this here, we know that if we were to take the slope of this, we would get some value. And here we'd get the same value times 2. So it's going to double the slope. So, for example, here where the blue line is like this, the red line, the slope would be twice as much. The same thing here. This is negative. And the slope, oops, we can't see it at this point, would be down here, but it would be twice as steep as it is here. Now, of course, here at 0 and 1, since the slope is 0, 0 times 2 is still 0, so the slope would be the same. But at every other point, the slope of the red line would be twice as much, 2 times the original one. So that's why we need to include, whenever we have this kind of setup, we have to include this number in the derivative because it does affect the slope. It does affect the derivative. Now, in trying to work on a problem, an application of this, so we're looking at sales in the U.S. after Christmas at a department store, and it's estimated that for the X day of January, the first day of January, the second day of January, sales will be, and it gives you the function s of x. Compute s of 2 and s prime of 2 and interpret your results. Well, if we're going to work with this, to find an s of 2, it's not too difficult. We can say, well, we're just going to put a 2 in for here, do an s of 2, and when we plug that in, we get 4. Well, what does that mean? An s of 2 here equals 4. Well, interpret your results. What does that mean? Since this is business calculus class, it basically means, well, what does that mean to you as a business person? Well, what is s of 2? Well, here, this is s of x. An s of x is gotten from here. For the X day of January, the sales will be. Oh, so this is sales. S of x is sales. So that's what the S means. What does the 2 mean? Well, the x here, the 2 is where the x is. So 2 must be equal to x, or x is equal to 2. Well, what is x? It's estimated that for the X day of January. Oh, so the X day of January would be the second day of January when x is equal to 2. So this means, in business terms, that the sales for the second day of January will be 4. 4 what? Is it 4 units? Is it 4 liters? Well, up here they did tell us that sales will be S of X. Oh, and it's in thousands of US dollars. So just from the problem, we find out what we need to interpret, what this actually means for business. So this is it's in thousands of US dollars. So that's going to mean that on January 2nd, the sales will be $4,000. So when we're building these kind of things, we do attempt to link this together so that it makes sense. It would not be good for you to go to your supervisor and he says, what's the sales for January 2nd? And you come back and say, it's $4,000, not $4. So you have to be careful with these kind of things. Now, S prime of 2. If we wanted to calculate S prime of 2, well, I guess we first need to find just what S prime is itself. To do that, we need to take our S and convert it into a form that we can use. So S of X is going to be equal to, well, still 3, but now we can split apart the numerator and the denominator again. So that's going to be plus 9 over 1 times 1 over x plus 1, and it's squared. Well, this is the same thing as 3 plus 9 times x plus 1 to the minus 2. Now we can take the derivative of this. So our S prime of x, we take the derivative of first 3. Well, that's 0, so we can just ignore, whoops, I'm in the wrong one. Here, this 3. The derivative of a constant is just 0, so we can ignore it. So we want to find the derivative of this. 9 times the quantity x plus 1, quantity closed, to the minus 2 power. So what I'm going to do is take this 9 and multiply it by this minus 2. So that's going to be 9 times minus 2 times, now again, here we have something inside an entire parenthesis raised to an exponent. So we used in the parenthesis just the original function itself, the x plus 1. X plus 1. And the power then is going to be 1 less than this. Minus 2 minus 1 is minus 3. Now we're not done, because we have done everything outside of this, but we haven't actually taken the derivative of what's inside of the parenthesis. So in this case it's easy, because the derivative of x is 1, and the derivative of 1 is 0. So it's just simply times 1. So we could say that this is going to be minus 18 x plus 1 to the minus 3. Now, we know that we're going to be asked, or we know that we were asked for what S prime of 2 is. So we have to convert this over. So we can say it's going to be minus 18 over x plus 1 to the third power. Make that a little bit better there. The minus 3 means we have to invert it over, and it becomes 1 over x plus 1 to the third power, and combine that with the 18. Now that we have the derivative, or we can use it with a number, then S prime of 2 is going to be minus 18 over 2 plus 1 to the third. So that's going to be minus 18 over 2 plus 1 is 3 to the third power. So that's going to be minus 18 over 27, which is, I'm going to convert it to a decimal. Of course, it's minus 2/3, but that's minus 0.66. Now, of course, it's all sixes, but we'll round it up to say it's 0.667. Now, I left it to 3 decimal places because we're working in thousands of US dollars with this. The second part of it was to say, well, what is S prime of 2? Well, what is S prime? Well, whenever we take the derivative, we're doing a rate, right? So that must mean the rate of S, which is sales. The rate of sales. How fast are sales happening? It's the sales rate. So the sales rate, now again, we're doing it here when S is equal to 2. So the sales rate on January 2 will be Now here it's minus 0.667. What does the minus mean? Does that mean that if the rate is negative, does that mean it's going up or down? Well, it goes back to slope. The derivative and slope are the same thing. If you have a negative derivative, that means it's going down. So the sales rate is going down at a specific amount. Now, again, the sales was in thousands of US dollars. So the sales rate is also going to be in the same unit, thousands of US dollars. So that actually means that this means that it's going down $667 per day, put the dollars up here, on this June 2nd. So maybe a better way to do that, and a much neater way to do it, would be to let the computer say what this is. That the sales rate on January 2nd is falling. It's going down by $667 per day. Now, working with derivative notation, we've been using this a lot. We know that this means that we're going to calculate the derivative, that it's a command to take the derivative, of course, too. And by changing the x and the t, we realize that we're taking the derivative with a different one. This is the derivative with respects to x. This is the derivative with respects to t. If we add something to the top here, this means the derivative of y with respects to x. So we're going to take the derivative of the function y, but when we do it, we're going to find the answer in terms of x's. Our answer will have x's in and not y's. So for example, if we had y is equal to x squared plus x, the derivative of y with respects to x of y, we would substitute in this x squared plus x for y. So the derivative of y with respects of x, which means using only x's, is x squared plus x. We can use other variables, of course, too, but we're using x's to take we're taking the derivative of the x's, and we take the derivative of that to get 2x plus 1. So if we had a function v equals 4t squared, the derivative of v with respects to t, we're going to use this, and instead of using x's, we use t's. So it's going to be 4 times 2, which is 8, t to 1 less power to 1, to the first power. So even though there's no x's there, because we're doing the derivative of v with respects to t, we do it in respects to t. Anything else that appears there, even if it's a variable, we treat as a constant because we're only taking the derivative of with respects to t, which means we only take the derivative of terms that have t in them. So for example, if we were taking the derivative with respects to t of this, what would this be? Now in this case, if this was 5x squared, we would say, oh, it's 5 times 2, it's going to be 10t. Well, the same thing happens here. We don't know what this is, but if we're taking the derivative with respects to t, this is the same thing as some constant, even though we don't know what the value a is. So it's a times 2, or 2a. So it's going to be 2a times t, t to the 1 less power. The second one, s, capital S, is some value. We don't know what it is, but it's some value. So we take s times minus 1 to get minus s, and we take t to 1 less power, which is minus 2. Now, s squared, again, it's actually a value. We don't know what it is. It is a variable, but s is going to be equal to something, and when we square it, it's simply a number. And the derivative of a number is 0, so it would be like plus 0 out here, but we don't need to write that. So again, when you're doing the derivative with respects to t, you take t as your variable, and you treat everything else as a constant, even if you don't know what it is. Now, if we have the same function here, and we do the derivative with respects to s, capital S in this case, well, there's no s's in this first term. So even though we don't know what a is, we don't know what t is, they're going to be some value, a constant. And a times t squared is going to be some number, and the derivative of a number is simply 0. So we don't need to use that. We wouldn't even have to write it. So this is some number. The derivative is 0. Doing the derivative with respect to s, t to the minus 1 is a constant. So it's going to be t to the minus 1. And now here the capital S is like it's to the first power. So when we subtract 1 from 1, we get 0. And of course, that's 1. So that's why we get minus t squared, or excuse me, t to the minus 1. When we do this, again, t to the minus 1 is some constant. Usually we're used to seeing it over here, and that kind of throws some students off. But remember, it's just a constant, so we take it times s to the r. In this case, r is 1. Now this, again, s is what we're doing, so it's going to be 2s to the 1 less power, which is 1. So when you're working with this, it gets a little bit confusing. The homework has a couple of problems to help clarify it. But any variable, if you're not doing the derivative of it, just treat it as if it was a number. Pretend it's a number and work from there. Now, if we take a derivative, can we take the derivative of a derivative? Well, yeah, we can. It's called the second derivative. So again, if we had some function f, we can take the derivative of it, and that would be f prime. Now we take the derivative of f prime, and that equals f double prime of x, or the second derivative. And all of the rules are exactly the same, so it's not hard to do. So if we had some function here, f of x equals x cubed plus 1 over x, we can find the first and the second derivative the exact same way. And in this case, we need to get f of x into a form that we can use. So that's x cubed plus x to the minus 1. Now we can work with this. The derivative of this, again, is going to be 3 times 1. It's going to be 3x squared. Now, the one that's invisible, so to speak, in front of here, 1 times minus 1 is going to make that minus 1x to the minus 2. And of course, we're used to writing it more as 3x squared minus x to the minus 2. So the same rules apply. And if that's true for the second derivative as it is the first derivative, then we can just simply do the same thing. Take the derivative of the first derivative, and you will have the second derivative. So now what we want to do is take the derivative of this. So this is going to be 3 times the 2, which is going to be, well, write it out the long way, 3 times 2, x to 1 less power, 2 minus 1. This is the same thing, the next term, it's the same thing as minus 1x. So this is the same, this is going to be plus, if you write it out the long way, minus 1 times minus 2, x to the 1 less power, minus 2 minus 1. So that's going to be, now we come back over here, 3 times 2 is 6, x to the first power, plus, oops, excuse me, it's going to, yeah, it still stays plus. The minus times the minus here gives us a plus, 2x to the minus 3. So it's not too difficult to do. We just have to use the same rules for the second derivative that we did for the first derivative. And any shortcuts that you did, I know a lot of students do these things in their heads. It's quite okay. Just make sure you get the right number on the exam so you get it all correct. Now, another example. Hopefully this is pretty clear, but one more just in case. We're going to take the first derivative of t to the 1/2. That's going to be 1/2 t to the 1/2 minus 1, which is going to be minus 1/2. Then we're going to, again, to find the second one, it's going to be this 1 times minus 1/2, which is going to be minus 1/2. T to the minus 1/2 from the exponent, minus 1 is minus 3 over 2. So that's the first derivative. Now, if you can do this in your head, feel free. In that case, you would take the 1/2 times the minus 1/2 and multiply it together to get minus 1/4. I'm just going to write it out the long way so that it's clear. t to the 1 of the power is 1 less than the one you started with, so it's 1/2 minus 1. Now here again, when you're doing this in your head, make sure you take into account the negative signs. If you're doing it in your head, a minus times a minus is a plus. 1/2 times 3/2, 3/4. And then t to the 1 less power. Writing it all out, we're going to subtract 1/2 times minus 3 over 2, t to the minus 3/2 minus 1. So that's going to be minus 1/4 t to the minus 3/4 plus 3/4 t to the minus 5 over 2. So again, the second derivative, use the same rules as you do the first derivative. It's just that you do it to the first derivative to get the second derivative. Now, the notation that we've been using, we haven't used all of them. Using both the prime notation and the Leibniz notation, again, the Leibniz is this d over d of x. When we're doing the prime notation, it's just simply f prime of x with the slash, meaning the first derivative. And of course, we've seen this before. If we were just doing y, it'd be y prime, and it would be the derivative of y with respect to x. Now when we do the second derivative, we put 2 of these slash marks, little hashes or whatever they're called, apostrophes. F double apostrophe, or f double prime, or the second derivative of x. With the Leibniz notation, they annotate it simply by putting a small little 2 above the d and the x here. So it's the second derivative with respect to x. So the 2's means the second derivative. And of course, if we're doing y prime, you would just say y with the 2 slashes, or the 2 apostrophes, and then with the Leibniz notation, you just put the y on the end. So it's still the second derivative of y with respect to x. So not hard. The first derivative with Leibniz is just that, and the second derivative puts the little 2 as an exponent, or looks like an exponent in there. Now, the other thing to be aware of, the notation that you'll see in the book and potentially on the exam, is that if you're doing f prime of a, that in Leibniz notation can be written as the derivative with respect to x, and oftentimes the function is listed, and then this horizontal bar when x is equal to a. And this means the same thing. Take the derivative of the function and then do when x is equal to a. Same thing with the second derivative. The second derivative at a, we know if we were doing this, we would calculate the second derivative in terms of x. F double prime of x is equal to some function, some equation. And then if a was equal to, say, 2, we would put 2 in here and find out what the value is. The Leibniz notation is written this way. Find the second derivative of the function and then put in the value of a, whatever it may be, in for x. And these two things mean the same thing. Now, giving a marginal cost, we started talking about the derivative also measuring marginal cost. Naturally, it could also be marginal revenue and marginal profit. In the introductory chapter, we said we defined the marginal cost as the cost of producing just one more unit, and it ignores electricity or any kind of overhead. So if we were building 15 items and A was 15, this would be the cost of 16 minus the cost of 15. And we would have what our marginal cost is. Now if we're graphing that, and this was our cost function, here, if we were doing production level of 15, and then this would be 16, if we wanted to find the marginal cost, we would find, in essence, the slope of this line in between, which, as you remember, is the secant line derivative, and in that case, h would be 1, the distance between here. Now we realize that the marginal cost, the cost of, again in my example, 16 units would be this, the cost of 15 units would be this, So the cost function would be just like we have above, C of 16 minus the C of 15. And since the increase is only 1 unit, that's the same thing as calculating the slope of the line, specifically of the secant line. The slope would be taking the change in y over the change in x, and the change in x is 1, so it would just be this over 1. Now, this also works out to be the average cost the average cost of producing 15 or 16 items, the average cost between the two. We'll talk more about this later. But we notice if we draw the tangent line here in the example I said 15, but here at A, if you drew the tangent line, whereas, well, it doesn't come in exactly up here at a C of 16, but it's really close to it. So we notice this and say that, yes, the marginal cost is calculated accurately this way, but if we want to estimate it closely, we can simply take the first derivative. This is the logic behind why we say if you want to find the marginal cost or marginal revenue or marginal profit, you can take the first derivative and it will be extremely close. Now, sometimes it's further away than other times, but it's close enough that we use the first derivative as marginal cost, or to find margins as a whole. So, whenever you see a problem in the homework talking about marginal cost, just take the derivative of the function at whatever value they ask you to, and you'll find the value that you need. So, an example problem, suppose the cost of producing X items is, and here's your cost function, and it's in litas. And currently, your daily production is 50 items. Now, what is the extra cost of increasing daily function from 50 to 51 items? Well, the technical way, the 100% accurate way of doing this would be to do a C of 51 minus a C of 50. So we have to put 51 in for here of all these numbers. When you do that, you end up getting 1090.755, and then do a C of 50, 50 cubed, 50 squared. Well, it takes a while, right? Well, it ends up being 1075. Calculators make it easier, but still kind of annoying. So somewhere around 15 litas and 76 centas is your marginal cost. Now, let's contrast that to finding our marginal cost when x is equal to 50 using the derivative. Well, if we find the derivative of this, it's going to be 3 times 0.005, which is 0.15 x squared, and 2 times 0.5, well, that's 1, so it's just minus x plus 28. Now doing a C of 50 is easier. It takes a little less work. We come out with 15.5 or 15.50, 15 litas and 50 centas, and we realize taking the derivative, it was close. It's not exactly perfect, but it's close enough, and oftentimes in business, just simply use that as marginal cost, especially when we have to calculate it quickly. So it's not exact, but it's close. And of course, if it's true for marginal cost, it's good for all of the margins, marginal revenue, marginal profit as well. And the homework, there's enough problems here you may want to get started before class, but of course this is also on Moodle and you can see it there.